boys and girls. I am Julius Sumner Miller, and physics is my business. And on today's program, our special business is the subject of energy and momentum, two of the great immutable ideas of physics, and we must make clear their difference. So, for my purpose, I go to the two cars again. You remember what we have in earlier programs? A large, massive car on wheels, and a smaller car, little m, on wheels, and they are on the tabletop, and they are connected by a sort of elastic connection of rubber bands. Now when I pull them apart, I store some elastic energy in the stretch spring, and there is a force then which is exerted on both cars. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our business today is the very special third law in Newton's three laws of motion. And to view it at least once in our lifetime in the Latin, I have it here. Lex 3. Actione contrariam semper et equalam esse reactionem. Now, if you didn't know any Latin at all, you'd see something in there about action and reaction. And indeed, that's what it sums up to be. Third law, to every action, there is always an equal and opposite or contrary reaction, or the mutual actions of any two bodies are always equal and oppositely directed. Now, a strange introduction to this law would be as follows. Consider me standing still and quiet on the earth, and I jump up in this manner. I ask, did you feel the earth recoil? And the answer is, it must be, it did indeed recoil, even though you may not have felt it. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our special business today is Newton's second law, the second law. Now, in an earlier program, we discussed the first law, and I showed you some dramatic demonstrations. On the first part, a body at rest, and on the second part, a body moving uniformly wants to do that. Now we come to Newton's second law. This is a staggering thing in its implications, and very, very difficult, really. But what students of physics learn somewhere in their course is that Newton's second law says F equals ma. And indeed, that's what it says. But that's powerful and not so easy. Let us see what Newton said for his second law. In the Latin, mutationem motus proportionalem esse vi motrici. But the Latin is a little old-fashioned, so if we look at the English, here it is. How do you do, ladies and gentlemen? I am Julius Sumner Miller, and physics is my business. And I should say, how do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our special business today is the subject of inertia. And I must make the matter, the idea clear, as follows. Here we have a block of wood at rest on the tabletop. And I ask, what does that block want to do? Answer, the block wishes to remain at rest. Supposing now I have double as much block, and I try in turn to put that system in motion. What do I discover? It also wishes to remain at rest. Moreover, it wishes to remain at rest twice as much, and therefore we say its inertia is twice as great. And so you discover at once that I have used the term inertia and referred to the idea of mass as synonymous. So mass and inertia are synonymous. And this is all tied up beautifully in Newton's first law, which says what? If a body is at rest, it wishes to remain at rest. And if it is moving uniformly in a straight line, that's what it wants to do. In English, simply, whatever a body is doing, that's what it wants to do. You see. Let's consider a stick, a meter stick. If it was a good stick, as I would like to have it, it would have to be uniform, homogeneous, and isotropic. Those are wonderful words to know the meanings of. Supposing the stick weighs 10 pounds. How do you do, ladies and gentlemen? I am Julius Sumner Miller, and physics is my business. And our business today is the idea of center of gravity. A marvelous thing to consider, really, and fantastic in its consequences for the human race. Consider the following. I have here a double track, which is downhill to my left. Here I have a cylinder of wood, which, as you know, will go downhill, as any respectable cylinder should do. But here I have another geometrical form, and I put it at the bottom of the plane, and lo and behold, it goes uphill. And that's a strange business. Well, friction forces are holding it there, so you see, it goes uphill. And a proper understanding of this lies in an understanding of center of gravity, an idea we got first from Archimedes in about the 3rd century BC. Consider. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our very special business today is the subject of freely falling bodies and bodies which are projected, projectile motion. And I would remind you of things already learned in earlier lessons, such as, for example, a body of small mass, a body of enormous mass, released to fall freely, released simultaneously to fall freely. And what is their behavior? They fall at the same rate. And you remember, it is Newton's second law that tells us that, namely that F equals ma, or for freely falling bodies, W equals mg. Now, what is the action of a body falling freely? Of course, it encounters in real life some viscosity and friction and trouble with the atmosphere. So what we can do is lodge a heavy body and a light one, say a coin and a piece of paper, in a tube, and then with a vacuum pump, take out as much air as we can, and then do as follows, and we would see both bodies fall at the same rate. I had this tube originally evacuated, but there has been a leak, so the experiment, as some would say, has failed, but I remind you, I have not provided nature with her requirements to show the simultaneity of fall of both bodies in free space. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our very special business today has uncommon enchantment, because the motion is beautiful to witness and wonderful to understand. We are going to talk about simple pendulums and other oscillating things. Consider the following. If we have a rigid support, and there are none really because everyone shakes however rigid, and we hang an ideal string, by an ideal string I mean a string that has no mass, no weight, has no inertia, has no tension, is perfectly inelastic, ideal mathematically, and we hang a small bob on the end, and we displace it from this equilibrium position and let it go, it oscillates as a simple pendulum. Now, we wish to explore its motion. When you study the lesson in this business, you will find that the period, which is the time for a complete trip, comes out to be some such expression with which I will not have much to say, about which I will not have much to say. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business, and my business today has most uncommon enchantment. And of all the things I like to do, of which there are hundreds in this business of demonstrations, this indeed enchants my soul the most. It has to do with the principle of Bernoulli. Bernoulli. B-E-R-N-O-U-L-L-I. And I urge you to go and read about the Bernoullis, because they were an uncommon family. 120 of them, all geniuses. unlike anything in the history of the humankind. The best that we've ever had are the Bachs in music, and there were only at most 24 of those. But can you imagine over 100 people named Bernoulli, all geniuses, not one an ordinary man? Now I will recite to you quickly and passingly the principles lying herein these demonstrations, which you can read about in your books. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business, and the physics today has uncommon enchantment and beauty. It has to do with soap bubbles and soap films and surface tension and why raindrops are round and other such enchanting matters. Let me do now, first on the blackboard, some introduction to the first experiment, which you will be enchanted by, I am sure. Let us consider a tea tube, so, with an arm here, and a little funnel or thistle tube there, and a thistle tube here, and let's say a rubber tube there, so I can blow some air in here by mouth. Now I am going to dip the ends of these funnels into some soap solution and blow some bubbles. So you see what has come to me in my 58th year, an old man, a physicist, playing with soap bubbles. But I have spent 40 years playing with soap bubbles and have not yet tired of it. So I'm going to blow 2 bubbles. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our business today has more than ordinary enchantment, and I will go at once to it. Consider the following. I have a tin can with some water in it, under which I have put a burner, so that the water has now been boiling for a time, as evidenced by the water vapor seen here condensed, and we call it steam, so that what remains in the vessel now is some water, less than before, and some water vapor. Now I'm going to take the burner away and stopper up the can, and we will witness an astonishing and absolutely astonishing thing. If we listen very carefully, we will hear a certain flexing of the can. What is happening? Some of the water vapor is condensing, the pressure is getting less in the can, and the atmosphere is taking hold. And atmospheric pressure is an astonishing thing. I will hasten the process by pouring some cold water on it. And this is an experiment you can do with absolute enchantment yourself. Here it is. I am going to take the burner away. I am going to stopper this up. I'm going to put it down here. Listen. Oh. But watch it. I'll hasten the process. Oh, there it is. Let me turn it around. There it is. And I say that is something to bear witness to. That is fantastic. The push of the air. Staggering in its consequence. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our very special business today is a very important subject, which is commonly referred to as centrifugal force. Centrifugal force. And I'm going to put the word centrifugal in quotation marks because it is so badly, falsely, erroneously, incessantly badly used. Illustration. Here I have a ball on a string, and I whirl it in a vertical circle. If now at the top of the path, let us say, or at the bottom of the path, I let it go, I cut the string, does the ball go radially outward from the circle? No, it does not. It goes tangent to the circle at the place in question, like that. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our very special business today is the enchanting phenomena associated with things that roll, rolling things. hoops and spheres and discs and the like. Consider the following. I have here a board which I can use as an inclined plane by raising it higher or making it lower, and here is a block of wood. We all know that if I raise the plane high enough, there comes an angle, there's a little stickiness there comes an angle at which the block slides. Indeed, if I had a block twice as heavy, we would find, if we explored it experimentally, that the block twice as heavy slides at the same angle as the one block alone. And I'm going to write the mathematics of that for you so you can have something to think about. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our business today is the classic adventure of Archimedes about the 3rd century BC, with some wondrous things to report. First, consider a body, a lead weight, which I hang on a spring scale, and the scale reads so much. I am not interested in what it reads, but it reads the weight of the body. Now let me submerge this body in a vessel of water, and we see a remarkable thing, a very remarkable thing. As I submerge it, the scale reads less and less and less, and I urge you to see that the weight is not resting on the bottom of the vessel of water. Accordingly, when I submerged the body, the water pushed up on it, provided a buoyant force, as we say, which Archimedes discovered in his classical bathtub experiment. Eureka, eureka, I have found it. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our very special business today is the work of the young Frenchman Blaise Pascal, a genius of the 17th century, who died at an early age, indeed at 39, but left enough for us to contemplate for a lifetime. And I urge you to read his life, written by his sister, La Vie de Blaise Pascal, the life of Blaise Pascal. Indeed, at the age of 12, he happened one day to strike a dinner plate belonging to his mother, and it rang out, and he was thus led to write a definitive paper on vibrating bodies. I urge you to go read about it. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our very special business today is the subject of simple machines. Simple machines. Now, when you study these matters in school, it is usually said that these are the 6 simple machines. The lever, or as some pronounce it, the lever, the inclined plane, the wheel and axle, the screw, the wedge, and the pulley. And I wish in this program to show that really all of these reduce to only 2, the lever and the inclined plane. And what is better for us to contemplate is the following, that all of the things I will have to deal with here today are the most plebeian and simple and homely and commonplace. And my purpose is essentially this, that when you pick up your fork and knife to eat your dinner, I hope you would recognize that you are using some levers. Indeed, the sharpened blade of the knife is an inclined plane in addition to the tool itself being a lever or lever. And how about the prongs of the fork? The prongs of the fork are usually sharpened a little bit, so they are wedges, and wedges are inclined planes. And so, ladies and gentlemen, and boys and girls, we come to the end of this program, indeed to the end of this 15th program, and what has been my singular ambition throughout the series. It has been just this, not to teach you any physics, not to assign any lessons or any problems, but rather to point up the beauty and the drama in all of this, and to excite your enthusiasm and your curiosity, for these are the foundations which will lead to your better understanding. Now, what have we done? What do physicists do? What is physics? What is science? That's an all-embracive term. Science, of course, is what scientists do. Physics is what physicists do. And what do physicists do? Physicists explore how nature behaves. And I urge you to spell that nature with a capital N. So as you go about your daily affairs, your school days, your days at home, your playing hours, I would urge you to have a regard for the things all around you, for they are filled with beauty and drama. And seeing how nature behaves will give you a full life. And I thank you for listening.